Hi everyone, my name is Elaheh Sadredini, and in this presentation, um, I'm going to present our work on privacy preserving computing on ABUMPIMP. So traditionally, we are using memories only to store data, and if the data is sensitive, then we can simply use memory encryption and decryption techniques um, to encrypt the data before sending and storing them into off-chip untrusted memories. However, if we are repurposing these memories for the sake of computation, then we need to store data, even sensitive data in the plain text in the memory. And this means that we are not able to perform computation with encrypted data when data is encrypted using conventional memory encryption techniques. And this work discuss how to enable confidential and secure computing on untrusted memories or PIM architectures, and we evaluate our solution on Augment PIM, but our solution can be applied to any other off-chip processing in memory architecture. Right, so for the security and privacy, TEE or Trusted Execution Environment is proposed to ensure the confidentiality and integrity of data and sensitive code by introducing the protected enclaves, and is a mature technology. And examples of the trusted execution environment are ARM Trust Zone, Intel SGX, Qualcomm Secure Execution Environment, RISC-V Keystone. And the data within the TEE and the internal state of the processor are protected from the unauthorized observation and modification. Also, any malicious software presented within the same processor cannot achieve or affect the private data. So, however, the off-chip component are in the TEE threat model are regarded untrusted. And that means that an attacker may attack to access the unencrypted user data stored in either standard or PIM-enabled memory, or making unauthorized modification. So the attacker might eavesdrop on the bus to extract sensitive user information or tamper with the data. The attacker might launch a cold boot attack on the standard DRAM or on the PIM-enabled DRAM to retrieve useful information or secret data. And there could be vulnerabilities or the backdoor on the that enables processing elements in the untrusted PIM accelerator to inject fault in the computation. Okay, so this is our threat model that we are considering. And we assume that only the CPU is a trusted execution environment and is trusted, and off-chip memories or PIM accelerators are untrusted. And all data offloaded and all the offloaded data needs to be protected by encryption. So if we enable the in-memory computing in our system, then we are performing computation in the memory or close to the memory. And that means that we cannot encrypt the data because the memory encryption does not support, the conventional memory encryption techniques does not support computation on the ciphertext. So the main question here is that how we can enable data privacy, data confidentiality, and integrity for in-memory or near-memory schemes, and that needs to be low overhead, because otherwise it's going to, if the scheme is going to have performance overhead, then at the end of the day it's going to cancel out the performance benefit that we are gaining from the processing in memory in the first place. So the computation cannot be performed in the conventional memory encryption techniques. So one way of enabling the computation and encrypted data is, of course, to employ homomorphic encryption. So although homomorphic encryption enables computation on the ciphertext, it's high computational complexity, and the high data bandwidth requirement ends up with having up to 3 to 4 orders of magnitude performance slowdown compared to the non-secure implementation. And an alternative solution might be including PIM within the trusted execution environment through a specific mechanism, and that is going to enable PIM to securely receive the plain text However, bringing the PIM architecture into the TEE required the redesign of the PIM module, for instance, introducing the internal root of trust or secure boot features, ensuring supply chain security, and many other substantial changes. Another approach is to leverage the secure multi-party computation and partitioning the computation between the PIM and trusted execution environment. So in this work, we are using a combination of arithmetic secret sharing and the counter mode encryption, so that the TEE holds the trusted execution environment, which is the CPU, is going to hold one share of the data, and the off-chip, untrusted off-chip processing in memory module is going to hold another share. And therefore, the untrusted party is not able to retrieve the original secret data from only one share of the data that it has. And because the untrusted party is going to have only one share of the data, it doesn't require the non-collusion assumption to hold among the processing element on the PIM modules. So, okay, so at high level, we are proposing to leverage arithmetic secret sharing in secure multi-party computation in combination with the TEE, or trusted execution environment. So I'm going to explain it using a very simple example. For the data confidentiality, to protect data confidentiality, and later I'm going to explain a little bit the integrity and verification checking for our scheme. Okay, so assume that we want to compute Z here on the in-memory architecture. Okay, so here the assumption is that so we are going to compute AX plus BY. And then the assumption is that X and Y are secret. Assume that X and Y are the input of a DNN model. And then X and Y are secret, and there are member of the integer rings, right? Okay. So we assume that the data is initially, so the secret data is initially encrypted in the memory using the conventional encryption techniques. So this is the initial state. And then the data is first read from the memory into the trusted execution environment, and then it can be decrypted so that we are having access to the plain text. And then using the TE counter mode encryption, we can generate the one-time path using the memory address and the version numbers. And then we employ the arithmetic secret sharing so that we, instead of doing the XOR to create the ciphertext, we perform the subtraction and subtract the plain text from these random numbers generated by the one-time pad to generate the ciphertext, so that we can later on retrieve the final result by adding the partial result that we are getting from the XR and YR computation, and then XC and YC computation, which is the random numbers and the ciphertext that are generated. So what we do is that we go ahead and send the ciphertext to the ABUMPIMP to compute the Z sub XC or the ciphertext or the cipher result. And then we send the random numbers, the XR and YR, into the trusted CPU to perform the same computation on the one-time pad or on the random numbers. And after the computation is done, then at the end, the results are transferred from the ABUMPIMP into the TE, and then the TE is going to add the partial results and then generate the final result. Okay, so what we are hoping here is that the computation on the CPU, so because we are performing the very same computation on the CPU as we are doing the same computation on the ABUMPIMP, what we are hoping is that the CPU part is not going to be the performance bottleneck in the computation, because these two parts are performing parallel, so that the only thing is added to the critical path is performing this gathering of the final result of the ZR and the Z sub C, so that we can generate a final result for the plain text and the trusted execution environment. And another thing to note here is that by sharing only one share of secret, one untrusted worker, which our assumption is that untrusted PIM architecture cannot recover the original secret. All right. So now the challenge is that both the CPU and ABUMPIMP, as I mentioned, are performing the very same computation. The workload is the same. However, the challenge is that the CPU has limited memory bandwidth, but it's good in performing the compute intensive workload. And at the same time, the PIM architecture has usually limited computational capability. And this, but they do not have issue with the memory bandwidth. And this make an issue with workload balancing and potentially making the CPU to be on the critical path. So in order to address this issue and provide a balance between the CPU and memory in a way that the CPU is not in the critical path, we are employing two approaches. So the first approach is that we generate these one-time paths, which means the computation that's performed on the CPU side on the fly, using the version number and the address, so that we can perform the computation on the X and Y sub R. And that means that because we are generating these one-time paths on the CPU on the fly, that means that there is no data communication between the memory and the CPU, between the system memory and the CPU. And that means that everything is going to be on the compute-intensive part of the spectrum on the CPU side, on the TE. But still, we need to bring the public data or the part of the data that's public to the CPU in order to perform the computation for the one-time path on the CPU side. And then the other approach is to use the pre-computation method on the CPU portion, and that can be applied only to a certain cases or scenario. And that means that we are performing this computation that's required on the CPU side offline. And whenever we launch the computation on the ABUMPIMP, we are bringing these pre-computed results from the memory to the CPU, and then we are waiting for the result to come back from the ABUMPIMP side so that we can merge the result at the end and generate the final result that we hope for. And this also avoids the CPU to be on the critical path or to be the performance bottleneck, right? So I'm going to go ahead and discuss this solution in a little bit more detail. So the first solution is when we are performing the CPU portion by computing or by generating the one-time paths on the fly. And based on our experiments, what we found is that this approach is going to perform well only if the size of the private data or the secret data is significantly larger than the public data. For example, if you're doing the matrix vector multiplication, so if the matrix is the secret data, then this approach is going to perform well. That means that the CPU is not going to be the performance bottleneck. And the reason for that is the larger portion of the data, which is the secret data, the computation for that part is going to be generated on the fly on the CPU using the one-time path. And there is no memory CPU communication to affect the bottleneck and make the CPU to be the bottleneck of this computation. And then, so in the, okay, I'm going to explain it in 3 stages. So in the very first stage, which is the initialization stage, ciphertexts are generated in the trusted execution environment by subtracting them from the one-time pad, and they're stored in the memory. So this step is can be performed offline so that we can generate these ciphertexts in the trusted execution environment and store them in the memory, and then we wait for start of the computation in the online mode. And then in the runtime stage, what happens is that on the CPU side, again, the one-time paths are generated on the fly in order to perform the computation for its own share of data on the CPU. And then the ciphertext that we previously at the offline mode, we store them in the memory. is going to be transferred to the ABUMPIMP to the CPU, of course, and then the computation is done concurrently on the CPU side and on the ABUMPIMP side at the same time. And then if the private data is larger than the public data, then the computation time on the CPU side is going to take less than the computation on the ABUMPIMP side. And again, because the CPU is good at performing the compute-intensive application, because we are generating all the secret data on the fly, then there is no need for the data movement from the system memory into the CPU side. And therefore, the CPU will not be on the critical path. And in this scenario, the only thing that will be again on the critical path is the final addition of the result that we are sending from the ABUMPIMP to the CPU. And then, okay, so coming back here. And then, so this is going to be our first solution that we are proposing, that how we can leverage the on-the-fly generation of the one-time paths in order to have the CPU to do its own share of computation, and then the ABUMPIMP to do its own share of computation. And then our experiment has shown that the CPU, when the secret is extremely larger, not extremely larger, but significantly larger than the public data, then the CPU is not going to be the performance bottleneck in these runtime methods. So we call it UPMEM runtime C. So the runtime refers to performing the CPU computation on the fly, and then the C refers to the confidentiality technique that we are employing here. For the second technique, we are employing the pre-computation technique. And that means that when the public data is larger than the private data, if you're having matrix vector multiplication, if the vector is the secret data and the matrix, which is larger, is a public data or non-private data, then it necessitates a larger data communication between system memory and the CPU to perform the CPU portion of the computation. And that's going to make the CPU portion to be the critical path if we employ the on-the-fly computation for the one-time path generation. And this is going to cancel out the benefit that we are getting from the PIM computation in the first place. And in order to avoid that, we are leveraging the pre-computation method on the CPU side. Again, in the initialization stage, which is going to be offline, we are going to generate the ciphertext using the one-time path that generated on the trusted execution environment. And then we are going to store them back into the system memory, and they are ready for the start of the computation in the online mode. Okay, so another thing that we are doing is to perform the pre-computation on the portion of the computation for the trusted execution environment. And that means that the CPU portion is generated at the offline mode, and then the result, and because you can generate the one-time pad using the address and the version number, it doesn't require any information for the input. And then we are generating these one-time pad, and then we perform the computation for these one-time pad. And then after that, we encrypt the final result, and we store them in the memory. All right, and that means that this method can only be applied when the public portion of the data, or in this example, if we are having matrix vector multiplication, and if the vector is the secret and the matrix is the public data, and then if the matrix is the weight and biases of the DNN, and they are known beforehand, so you can go ahead and perform that part of the computation and the one-time pads for the CPU portion, and then store the final result, or the Z sub E, in the memory. So you can encrypt using the conventional memory encryption techniques, and then encrypt the result, store them in the memory, as we can see here. And these method can be commonly employed in the DNN inference. And again, because if you assume the input is secret and then the weight are public, then we can easily perform the pre-computation on the CPU share, as the weight and biases are known beforehand. And then this way we have pre-computed everything on the CPU portion, and then making sure that the CPU will not be in on the critical path. And then on the runtime stage, the ciphertext that we had generated in the at offline mode is going to be sent to the ABUMPIMP side, and at the same time, the CPU is going to retrieve the final result, or the Z sub E, from the memory into the TEE, and it's going to decrypt it, and it's have the result ready sitting there. And then for the CPU portion, and then the ABUMPIMP side is going to perform the computation on the ciphertext, the same computation as we initially had to do without considering any security scheme or any data confidentiality scheme. And then at the end, we are going to combine the result from the ABUMPIMP and the TEE on the TEE side. And then using this method, what we are having on the critical path, in addition to the base computation that we initially had on the ABUMPIMP side, is to adding the final results Z sub R and Z sub C to generate the final result on the CPU side. So this is the two data confidentiality scheme that we have employed, and depends on the size of the input and the secret size. The secret data, sometimes the on-the-fly computation is not going to perform best, but the pre-computation method, when it's possible, is going to avoid the CPU to be the performance bottleneck in the computation. So the final execution time is going to be very close, as if we didn't have any security scheme in place or data confidentiality scheme in place for the untrusted off-chip processing in memory architecture. And then for the sake of comparison, we also consider another scheme and another scenario, which we call it, which we are calling it the ABUMPIMP encryption decryption scheme. And in this scenario, we assume that the off-chip PIM is completely trusted. So there is no backdoor Trojan, or there is no cold boot attacks. But still, this interconnection between the CPU and the off-chip PIM architecture is going to be untrusted. There's still bus snooping attacks going on. And that means that we can expose the plain text to the off-chip PIM, but in the interconnection, it needs to be encrypted. And that means that in this scenario, the data is initially encrypted in the memory using the conventional memory encryption scheme, like as usual, as normal. And then in the runtime, we are sending this encrypted data from the system memory to the ABUMPIMP, and then ABUMPIMP receives all these encrypted data. It decrypts the data, and then it has access to the plain text, and it can perform the computation on the plain text. So this way, we are dealing with the bus snooping attack, and we assume that the off-chip PIM is trusted, so that the plain text can be exposed to the off-chip PIM. Okay, and this is another scenario that we are performing the comparison with. And we are calling it the ABUMPIMP encryption decryption scheme. And then for the verification scheme, we are employing the message authentication code in order to verify the integrity of the data and computation. So verify the computation at the end, making sure the data hasn't been tampered with or the final result hasn't been tampered with. And in order to do this, a linear checksum or a hash function is used to generate the tags. And then we encrypt the tags based on the data confidentiality scheme that we are having in place. And we store these data, we treat them as the secret data, these tags, and then we store them in the memory to be used later. So for example, assume that here's the matrix that is our plain text data, which needs to be protected. And then we generate the linear checksum. And then that's going to be one tag per column. And then we encrypt these tags in the TEE and store them in the memory, similar to the computation as the data will be performed on the tag. And then after performing the linear checksum over the result, we can compare the new tags with the tags that are retrieved to verify the result, making sure that the integrity of the data hasn't been changed. All right, so to evaluate our data confidentiality, integrity, and verification, we are using the ABUMPIMP server. So we all are already familiar with the detail. So we are using the 20 PIM enabled beams. And then in order to compare it with the CPU insecure, assuming that the CPU no security scheme, and then the CPU security scheme, we are, in order to calculate the overhead of CPU secure implementation, we are leveraging the Google Cloud and AMD secure encrypted virtualization mechanism. On the application side, we are evaluating on the MLP inference stage, which is employed from the prime benchmark. We are evaluating on the DLRM on the inference stage, employed from the base implementation, employed from the UBC group, and then the logistic regression training, where the base implementation is adopted from the PMML benchmark from the Safari group. So here, the first set of results that I'm going to present is going to be for the MLP, different model sizes. So here, the assumption is that the GenV kernel is securely offloaded to the ABUMPIMP, and the nonlinear activation function is performed on the CPU side for the secure scheme that we are considering. But non-secure scheme, similar to the base implementation, the nonlinear activation function is going to be performed using approximation on the ABUMPIMP side. So the x-axis here is showing different model sizes, and then the y-axis is showing the execution time in log scale. And then first we are having the CPU implementation that doesn't assume any security assumption. Then we are having the secure CPU implementation based on the AMD secure encrypted virtualization. What we are observing is that there's not much performance overhead when we are using not the SGX, but the secure encrypted virtualization. And then we are having the ABUMPIMP insecure, and ABUMPIMP insecure is the base implementation, which doesn't assume any encryption or the data confidentiality, integrity, or verification scheme. And what we are observing is that as the model size increases, the ABUMPIMP base implementation achieves up to 14 times speed up over the CPU insecure implementation. And then we are having ABUMPIMP encryption decryption technique. So the one that I just explained, that simply assumes that only the bus is going to be, the bus snooping is going to be the threat, and then ABUMPIMP chip is going to be trusted. And then we are having the ABUMPIMP encryption decryption technique using the verification scheme to make sure that the result hasn't been tampered with on the bus, which we are showing you with -V, which stands for the verification. And then we are having our pre-computation technique on the data confidentiality. C stands for the data confidentiality here. And then we are having this purple one, which is the computation technique, which employs both data confidentiality and verification scheme. And of course, it has a little bit more overhead compared to only data confidentiality because of the verification scheme is going to take a little bit of time. And then we compare them with the runtime method. So here, the observation here is that the runtime method is going to perform much worse than the pre-computation. And the reason for that is the secret data here is the input, and the public data are the weights, so that the secret data is much smaller than the weight, so that requires and necessitates a lot of data communication between the CPU and ABUMPIMP. And that's going to be the performance overhead for the runtime approach. But within all of these methods, our pre-computation method is going to perform very close to, the performance is going to be very close to the ABUMPIMP insecure or the ABUMPIMP baseline implementation. And that means that this security scheme is not going to add performance overhead on top of the base implementation of the ABUMPIMP for this application. And then the next one is comparing MLP across different batch sizes. And then what we are observing is that, again, because the public data is larger than the private data or the secret data, CPU is going to be the performance bottleneck in the runtime method. And again, the pre-computation is going to be the best method here with a very negligible performance overhead compared to the insecure baseline. For the DLRM, So comparing the baseline ABUMPIMP implementation, the third blue line, increasing the embedding table size, of course, is going to improve the ABUMPIMP implementation, the baseline over the CPU. And then applying the rest of the techniques, what we are observing is that the pre-computation and the runtime method is going to perform similar. And the reason for that is the secret data now is going to be the embedding lookups. And because the secret data is very large and the CPU portion is not going to be the overhead, and that means that pre-computation and the runtime method is going to perform the same, and they are going to have the same performance as the ABUMPIMP insecure or the ABUMPIMP baseline implementation. And then, so the last sort of result I'm going to present here is for the logistic regression training. And so we evaluated logistic regression with different model sizes, where the all linear function will be uploaded to the ABUMPIMP, and nonlinear functions will be performed on the CPU side for the runtime and pre-computation method. And so as we can see, so when we are increasing the model size, the ABUMPIMP baseline is going to perform better than the CPU. And then for the larger model, the overhead of runtime method is going to be much lower than the ABUMPIMP encryption decryption technique. And this is because the size of secret data here is very large, and that means that the ABUMPIMP encryption decryption technique requires a lot of encryption, a lot of decryption on the ABUMPIMP side, whereas on the CPU runtime method, the CPU portion of the secret is generated on the fly with minimal communication overhead. And it's important to note that in the training, because the weights are not known and fixed beforehand, we are not able to perform the pre-computation in the offline mode. Okay, so that's it. Any question? I'm happy to take questions.